Fantastic panel, and I cannot wait to get to it. Sonya Gavankar is a communicator who uses dynamic storytelling techniques as a spokesperson, television and podcast host, filmmaker, and social multimedia content creator. Her voice is divine. Just wait till you hear her voice as she moderates the panel. And she's been seen on ABC, PBS, and many others. She's launched something called herexchange.com, which brings a new perspective to insightful conversations and professional development tools that could be written word, podcasts, and live workshops. You guys are in for an incredible treat. Let's bring Sonya and her panel onto the stage. Let's give them a big round of applause. Come on.
Thank you. That is quite the build-up, especially early in the morning to say that I have a great voice. I would like to give credit to the whiskey tasting last night. Any dulcet tones you hear this morning. We do have an incredible panel to kick off this morning for you and for our live stream. I want to introduce you to everybody. Starting here to my left is Ruth Hemmersbach. She is DLR, Head of Divisions of Gravitational Biology, Vice Director of the Institute of Aerospace Medicine. Thank you for being here, Ruth. Julie Robinson, NASA JSC Chief Scientist, ISS. Dan Buckland, Duke University, Assistant Professor of Emergency Medicine and Mechanical Engineering. I should call you Dr. Dan, I feel. You earned it. Lisa Pratt, NASA, Planetary Protection Officer. And Saralyn Mark, NASA White House and HHS former Senior Medical Policy Advisor, iGIANT President and Founder. An incredible panel. Lots of experience and varied experience, so we have a lot to cover. We're going to ask each of you to present briefly on your topic of expertise. Then we will open it up for questions here and with our audience here in our grand theater. So we'll start with Ruth.
Okay, Sonya, thank you for the introduction. Can I have the first slide, please? It's the second one. Sorry. Okay. So it's the first summit, Mars Summit, I participate, and I really enjoy it. It's our great panels and experts, and there's a lot of time for very fruitful networking. And I want to bring in another aspect, life science, because if you want to bring men, women to Moon and to Mars, that they stay there, live there, work there, and we want to bring them back healthy to Earth, we need a lot of knowledge from life science. And we, at the German Aerospace Center in Germany, the Institute of Aerospace Medicine, we are working on these topics for many years. So we have a lot of experience, and our vision is also to keep astronauts healthy and improve human performance. And I want to stress on 4 points which are very essential, which we have to study and manage to bring men, women to space. The first aspect is radiation. And here we have done a lot of studies, and we are currently doing exposing microorganisms or material to the harsh environment of space. And there we can check the survival. You see on the left this biopen facility with microorganisms, and on the same time we measure radiation, what they experience. And what you see on the right, it's now a matryoshka, it's a phantom of the human body, and there we measure the impact of radiation on the human body. And you see on the right there is the matryoshka with a shielding, with a vest. So, and the other one has none. So this female matryoshka is going to fly on Orion. So, and I think it fits very well what we heard from Jim Bridenstine to bring a woman on Moon. So we have a female matryoshka. And the other aspect where we are also have experts in the Institute is Astro and Microbiology. And you see this ugly picture on the right, it's from the ISS, and you see there's a lot of biofilm, fungi, bacteria, and they form biofilm. And so far we do not know how, we at least know a little bit how bacteria and fungi will behave in space. And they form these layers. You have them also in hospitals as a problem. So in space they are one point for the human health, but also for techniques which have to be overcome. And also, that's the point for planetary protection, but we have also an expert here for this field. So the third point I want to stress is waste management. You can't bring all the food to space, so we have to think about how we can use waste. And you see here a filter system. It's a CROP, which we have developed in the DLR. It's a combined regenerative organic food production. And you see this filter unit, it's a biological system, and we put in urine. It's a typical waste, what we humans produce. And there's a consortium of microorganisms and which degrades the urine, the waste, into water and nitrate. And the nitrate, again, is used as a fertilizer for plants. So we can then produce from waste resources for feeding. And on the right, you see the EuroPis mission. It's a compact satellite which has launched on the 3rd of December. And it's built up also by the German Aerospace Center. And in this compact satellite, the name is Euglena and Cropis, so it's the filter we developed. Euglena is a small algae which produces oxygen. And so we test here, it's a pilot test to see how such a regenerative system can work in space, but not in space because this satellite is rotating. And at the moment, it produces moon acceleration, and later on it will spin down, and then it will spin up to Mars acceleration. So we have a proof of concept how such a filter system can work. Currently we have the experiment from NASA, from Lynn Rothschild, on board with bacteria, synthetic biology. And we have RAMES, it's a radiation monitoring system. So for the first time, we have a very continuous measurement of radiation in an interplanetary area. So what will experience men, women, when they are traveling between the planets. So we can measure this radiation. So, and the fourth point is human health and performance. We know and we need the testbed ISS to study the impact on the human body. And here we have, for example, the Sarcolab experiment running, looking for muscle degeneration, because this is also a problem in space, that muscle bone decrease. And we have the cardiovector experiment currently running, looking for cardiovascular deconditioning, which is also a point how the heart works. There are different conditions. They must not have so much strength like on Earth with gravity. And we develop countermeasures like artificial gravity. You see here on the right the human centrifuge, which we have in Cologne. And we expose humans there to test whether artificial gravity might be a good countermeasure. Coming to the end, I think it's not only necessary to do these experiments in space, we have to use our facilities and possibilities on ground in analogs, doing partial or simulated microgravity experiments. And here we have the ENVI Hub. It's our research facility in Germany, in Cologne. Here we can investigate humans under very controlled environmental conditions. We can change light, atmospheric conditions. And currently we are doing a bed rest study. And you see here Jim Bridenstine, he visited us some time ago. And if you look at the bed, you see it's not in a horizontal position. It's 6 degrees head down tilt. And the head is lying head down tilt. What happens? It's not microgravity, but the body experiences, like in space, a fluid shift. And the result is an increase in intracranial pressure. And what we see, obviously, a change in the visual system. So, and this is also a problem for astronauts, for the eyes, changes in the retina. So currently we are doing this study together with NASA and ESA, the EXPRISA study, artificial gravity in combination with bed rest. So half of the test systems are exposed daily on a centrifuge for training. The others stay completely all the time 60 days in bed We have now half-time, and it's running very well. They are in very good mood and condition. So I think we should also use all facilities on ground. This ENVI hub is next to the European Astronaut Center, and in between the ESC, the ESA are currently building a lunar facility. So where we can do a lot of studies on the topics I mentioned, also human interface interaction. So I think that's the topic, forward the moon on the way to Mars and back to Earth. That's very important to bring them really healthy back to Earth. And well, as Jim Bridenstine told, we should work together, and we offer our collaboration.
Thank you so much, Ruth. Facebook keeps telling me about, this sleep laying down study, and 60 days in bed sounds like a dream job. So if you need to fill a bed, please give me a call. Julie, please tell us what you have brought us.
Well, thank you so much for inviting me to speak with you today. I have just finished a year away from my day job as chief scientist for the space station and spent that year as associate director of NASA's Human Research Program. So that's given me the opportunity to really understand in depth the breadth of our research and to represent that program today. Of course, our Human Research Program is a risk-based applied research program, and as we look at the risks for all the different design reference missions that could be done in exploration, the most significant set of risks are for a human mission to Mars. And those include both the biological, the physiological, and the psychological challenges that could come during and after that mission. We like to look at exploration missions in a cohesive way, and we think of there being 5 basic hazards of human spaceflight. The first of these is space radiation from galactic cosmic rays as well as solar particle events, which have to be managed quite differently. The next is isolation and confinement from being in relatively small volumes with a small number of people. The next is the distance from Earth itself, meaning you can't necessarily come home. You cannot get resupply. If you discover you left something back home that you need, you don't have any opportunity to get it. And autonomy is required because of the communications delay on a mission like a mission to Mars. The fourth one is altered gravity. And in fact, there's been a huge amount of research on the International Space Station over the last 20 years, really focused on the effects of altered gravity, both being in a microgravity environment, which is a model for a Mars transit, as well as the gravity transitions during launches where you leave Earth's gravitational field, and then after landings when you return to a gravitational field. But as lunar missions develop, we also have the opportunity at looking at 1/6 gravity and trying to understand and predict what 3/5 gravity would be like. So, and then next is the hostile closed environment of space. So in these canisters, we come with a whole ecosystem. It's not just the human organism, it's also the microbes that are commensal with our bodies that we need to be healthy, as well as perhaps some microbes that are not as friendly to us that could cause illness or disease. And so looking at that hostile closed environment, also the CO2, recycling in our life support systems, all of the oxygen, scrubbing out carbon dioxide, all of those aspects of the hostile closed environment can affect human health. One thing that's quite interesting is early in the Human Research Program, we kind of categorized our responses to these in swim lanes, if you will. For example, the physiologists were mostly interested in altered gravity. We had a separate group of people that were mostly working on radiation. But as we start understanding and being able to predict and modify some of these hazardous effects on human health, we also wind up with the human becoming a much more integrated system, and these 5 hazards being a focus of really what are the synergies. For example, what are the synergies between space radiation and the brain, and how do those affect behavioral performance as well as physiology? So when we look across these different hazards of human spaceflight, and if you look at it from a perspective from Mars, looking back at that little tiny dot that is Earth, in altered gravity fields lead to things like balance disorders, fluid shifts and visual alterations, cardiovascular deconditioning, and muscle atrophy and bone loss. However, not all of these are equally high risk today as they were 15 or 20 years ago, because we've made substantial progress on the International Space Station. In radiation effects, we think about both acute in-flight effects, long-term cancer risk, and central nervous system and cardiovascular effects. We look at vehicle design, the environmental system, the food and nutrition system, the isolation and confinement effects on behavior and sleep, and communications and autonomous medical care. As we start looking at lunar surface research operations, definitely depending on the mission design and duration, we can use lunar surface operations as a way of testing some of our approaches to Mars surface operations in the future, including autonomous egress and post-landing operations and long-term habitation and exploration on a planetary surface. And we have a major effort going on, which I had the opportunity to talk about yesterday, working with ISS and some of the Mars planning teams to look at what new things could we do on ISS that are more innovative and help to be more operationally relevant to Mars mission landings, including what we might do with crew members that are deconditioned, landing from the International Space Station in our future commercial crew landings. We've done substantial work with our Russian colleagues on the deconditioning and that effect on performance of crew members that land in Kazakhstan on the Soyuz. So just to summarize then, NASA's human research program, we juggle the things that we worked on based on the largest risks. Some of those risks are related to radiation acute effects and behavioral impacts as well as cardiovascular impacts. Some of the things you may have heard were the biggest risks to Mars are not rated as high anymore as they used to be because of the substantial progress we've made. Other things that people didn't even know about 15 years ago, like impacts of microgravity on vision, are still being investigated. And as we work together, we work to close these risks just like we would any of the other engineering systems, and to be ready so that the crew can safely transit to Mars when the agency is ready to go. Thank you.
Thank you so much, Julie. Dan, no slides, but great presentation.
All right, that's some confidence. All right. So, as I said, I don't have any slides. I use my hands a lot, but they don't actually mean anything. It's more for me than you guys. But as introduced, so I work as both a emergency room doctor at Duke University Hospital, and I have a lab in the mechanical engineering department at Duke, where we do medical device development. Me and my students work on finding problems that I find in the emergency room and say, how can we fix this with technology? And then the application to Explore Mars and the Mars is, I approach problems slightly differently because I work both in clinical in the emergency room and in mechanical engineering. And when we eventually do get to Mars or want to explore it in a sustainable way, it seems to me it'd be a tremendous waste of potential of the American educational system or the international thing if the best botanist or the best geologist who can do the work, who has to be at Mars, but unfortunately can't go because they happen to be diabetic, which is the current model of space medicine is you take the healthiest people you can, so you limit the amount of medical problems you have. But that limits the kind of people who can go and do the kind of experiments and studies that you want to have happen on the surface. So I look at it from what kind of technology can be brought to bear to expand the base of the health problems that can be brought to out to Mars or to any exploration environment. And so NASA has looked at this in a while, and the way this works in a logistic capacity is we get people like Julie who develop the risks and requirements for what needs to go out there. And then in the university and the industry world, we say, okay, thank you for developing a problem and the requirements for it. And then me and my students will look at those problems and say, okay, how do we address this in a clinical and a engineering capacity? And something that's happened and been noticed at NASA in the last 20, 30 years is NASA's a great place and the space agencies are a great place where engineers, clinicians, and life scientists all have to work together to solve these problems. But in the last couple of years, also noticed that this idea of you get a bunch of smart people in a room and great things happen is true, but a lot of people will leave that room thinking other things, thinking separately what happened in that room. Because when you have the experts in clinical science and in engineering and in life science, they use the phrase I like to use is everyone is speaking different languages, but unfortunately they're sharing a vocabulary. And so people say words like we're going to test this or we're going to explore this. And to an engineer, a test is it's a multi-day process that gives you an envelope and confidence intervals and process. Whereas as a doctor, I'm saying, I'm going to test your blood pressure. That just gives me a number, and it takes a minute. And so you have different experiences and expectations of what these processes go, and that leads to project failures. And so what in the last, about a year or two ago, the chief health and medical officer of NASA, the former one, wrote a book with a bunch of NASA experts and that I helped write, that is available because it's a NASA document about how engineers, life scientists, and clinicians can all work together, and failures that NASA's had that recognizes and when these different expertises with the best intentions just are not able to get the concepts together. And so that's the kind of space I work in, is how do these different specialties work most efficiently together to solve the problems to get humans out beyond the Earth.
Thank you, Dan. Lisa?
Thank you. I'm speaking of vocabulary and changing vocabularies. I'm gonna have a little shift here from the other members of the panel. My role is yes, to worry about the humans, but first to worry about the impact on life in general. And that means both terrestrial life, which we are starting to know on Earth, but we certainly don't know everything about it, and the life that we might encounter in another planetary environment. So there are two things in planetary protection that we worry about, and they're listed at the top here, and that's to avoid transfer of terrestrial life to a habitable world. There are three worlds we worry about right now: Mars, Europa, and Enceladus. And then, even more importantly, to prevent release of an extraterrestrial life or life form, or even just biological agent, on Earth during sample return. So we spend a great deal of effort, and we have a large number of people involved in verifying the biological cleanliness of spacecraft that we are launching to those three places, and it doesn't matter if it's landed or orbiting. We're concerned, of course, with orbiting spacecraft having an unintended crash on the surface and an unintentional contamination. That we usually work probabilistically. For anything that is going down to land or rove or actively explore, then we actually have a metric for determining biological cleanliness, and we do that by counting hardy spores, which is a technique that was developed at the time of Viking, and it continues to be sort of the gold standard for cleanliness measurements. But we also put a lot of effort into funding research that will get us ready for the next steps, the steps that involve humans. So our technology development priorities right now, and that means the tools we wish we had already. One is the ability to genomically or metabolomically characterize the terrestrial organisms that are hitchhiking on our spacecraft. We don't know who's there. We have a general metric, and that's the standard spore assay, but we don't know much about the ecology of organisms that can survive in a clean room assembly facility and get on a spacecraft and launch, and we don't know how the biocidal effects of transport in space reduces that community, or maybe selects for certain organisms. We need a tool that's better than the NASA spore assay, which is time-consuming and very dependent on the humans that do it. We need innovative chemical and spectral tools to detect bioburden on our spacecraft. And finally, we are now starting to work very closely with the healthcare industry and the federal health agencies on sterilization for use on a putative extraterrestrial organism. I just want to take this moment to remind you that we've had a revolution in our understanding of life on Earth that is by no means completed. We're right in the middle of discovering the diversity of life on Earth, and this image is a particularly nice one. I don't know if you can see the little red dots that are out here on the feather tips of a great many of these branches that indicate individual lineages of life on Earth. There's a lot of red dots, and those are organisms that we only know from their environmental genomes. We've not cultured them or grown them or imaged them, and that's a shocker, because you can see there's an entire region here of organisms that we didn't previously know existed. So it's concerning that we're still trying to understand life on Earth at the same time that we're preparing for a potential first encounter with life on another planet. So we ask ourselves all the time, Is there life present on the surface or the subsurface of Mars? And this is a marvelous figure from Clifford. He's shown this a number of times, and it sort of expresses the uncertainty of what might be below the surface of Mars and where we might encounter vapor caves or saline groundwater that could certainly be habitable in the way we understand life on Earth. And of course, with the recent discovery of perchlorates and other abundant salts on Mars that have an enormous freezing point depression, we realized that we could have liquid brines at much colder temperatures than we would naturally encounter them on Earth. And that means we have to worry in slightly different ways about both that forward contamination with a terrestrial organism or bringing back a sample that could plausibly contain something living or active from Mars. So we're getting ready for the biggest challenge we've faced so far, and that's sample return from Mars. And we absolutely, the number one objective is to prevent biological contamination of Earth. This is a very complex architecture. It's an integrated campaign involving elements from NASA and ESA, in which the rocket that we will launch carrying the Mars 2020 spacecraft next year will be the drilling, collecting, caching rover, and then later we'll send a small fetch rover to go pick up the sample tubes, and we'll transfer those samples to an ascent rocket, and we'll launch the sample container into orbit, and then there'll be a waiting spacecraft that will pick up the sample and return it hopefully to Earth for study here in our most advanced laboratories. That means we have to have in place safe handling protocols and procedures for a sample from Mars, because frankly, although we have not detected life on Mars, we have lines of evidence that indicate we need to be very prudent and be prepared for the possibility of contact with an active form of life from the subsurface, or, for me, even more interesting, the possibility of a dormant form of surface life that could be transferred around the planet or transfer into the ascent rocket from dust. So we think about three basic principles in terms of safe handling: break the chain of contact with Martian dust, have extremely robust containment of the samples as we bring them back to Earth and land them, and finally, be prepared for sterilization of an organism that we don't even know what that organism might be, but we assume that it shares some of the biochemical properties of life on Earth. How soon could this happen? Sooner than you might imagine. The timeline right now to bring samples back is the early 2030s. So we only have about 10 years to get ready, and in fact, we only have about 3 or 4 years to mature our understanding of how we will do safe handling. The great thing about a sample return from Mars for human missions is that we will demonstrate ascent of a rocket from Mars. And as somebody said a few minutes ago, if we're sending astronauts, most of them are going to want to come home, and that's going to be a tricky thing. We'll be developing sterilization modalities jointly, again, with industry and health agencies for what we believe to be a plausible form of an extraterrestrial organism. And then we will have, if this is successful, the remarkable thing about sample return is the inside of the sample container, which is about this big, there will be 20 or 30 hermetically sealed titanium tubes that will contain unsterilized sample material from Mars that we can use for advanced biological study. And we'd really like to know before we send humans if we think there is anything biologically active in the dust that moves around, very aggressively moves around the surface of the planet. And finally, of course, we'd like to be able to chemically and physically characterize the Martian dust, which will have an intimate contact with our astronauts, regardless of how carefully we try to control and filter air. So with that, I'll turn the clicker over.
Saralyn, close us out.
Great, thank you so much for the opportunity to be here today. I think it's quite appropriate that we're actually at the National Academies when we talk about sex and gender-based healthcare, because it's at this site that there was the genesis of this whole realm of science and medicine. In 2001, allergies in Washington, D.C.
It's fun that we're talking about what spores are out there on Mars, but we're all deeply affected here in Washington by what's
living
here in the
on this
swamp.
planet. We could study D.C. for that. In many ways. In 2001, the Institute of Medicine released a real seminal report entitled Does Sex Matter? And of course, the answer was yes. They also defined sex as the biological construct, really looking at it at the DNA chromosomal level. They defined gender as more the psychosocial construct. After that report, NASA decided it was time to actually do a review, to data mine what we had to look at sex and gender from every aspect that we had available. And you may wonder why this is important. Well, in a way, space is the most extraordinary platform to study sex and gender-based differences. When the body goes into space, as we've heard from some of my colleagues, and you've heard over the last few days, the body adapts very quickly and very dramatically. So very small differences can be detected, and those small differences may actually have profound and dramatic impact. We've had 2 surveys of our data, 2 reviews. One was in 2002, and a second review was conducted in 2014. That was conducted shortly after the IOM, or the National Academies of Science, as it was called now, developed another study looking at NASA's research portfolio. And we felt it was time, it had been a decade, to really assess what we had learned and where we need to go. What you have here is a diagram of our male and female astronauts. And as you can see, and it may be hard from some in the back to see, but every system in the body undergoes very dramatic changes. In 2014, a report was published in the Journal of Women's Health. It's available, anyone can download it, where we had convened 50 scientists from across the nation. We divided them into 6 work groups, studying every aspect of the body. So we evaluated the cardiovascular system, the neurosensory system, the immunological system, the reproductive system, behavioral health, as well as looking at musculoskeletal. The report was published, and it really generated a great deal of interest, certainly not only from our fellow scientists, but also from the media. Because some of the headlines were, does sex matter? Who's the stronger sex? And we wanted to be clear that this was not a battle of the sexes. It's not a question of who is better, who is stronger, who is faster. It's that there are differences, and through these differences, we can develop better countermeasures and better preventive measures to keep our astronauts healthy in space and when they return to Earth. You heard this morning about some key changes that happen in the body and some key findings, and I just want to highlight a few of them since I think I have about 2 minutes left. One of which is the visual impairment intracranial pressure syndrome, which is what our report called it. Now it's called SANS, Space Adaptation Neurosensory Syndrome. And what we have seen is that both male and female astronauts have changes on their scans, revealing that there are changes in the eye structure. Interestingly, it's our male astronauts that are the more symptomatic. And we're trying to discern the reasons for this because this is a significant issue. You're going into space, or you land on a planet or the lunar surface, you need to be able to see what you're doing. We think this may have some relationship to the younger age of our female astronauts who are flying, as well as the hormonal milieu. We know that estrogen is a vasodilatory type of agent, so that there may be greater compliance, and our female astronauts may not be as symptomatic. In regard to radiation exposure, this is an interesting area. Currently, our female astronauts have rates of exposure that may prevent them from even going to Mars if we don't develop better countermeasures, better, safer habitats to prevent the issues that we discussed, such as cancer, as well as other issues. Behavioral health is a very important one, and it's often negated and neglected when we talk about healthcare, but we know it's so critical. Traditionally, women have had the friend and befriend aspect when they're dealing with stress, whereas some of our male colleagues have more of the fight or flight. And I think in a mission to Mars or the moon, there really isn't anywhere where you can flee to, and you certainly don't want to fight. It's often been discussed that single-sex or single-gender crews tend to get along better. It's easier, and that may be true up front. There may be some more challenges getting crews who are mixed gender to get to know each other, to work effectively. But just as we see with our life here on Earth, diversity really has significant value, and it really impacts our performance, greater work performance and greater outcomes. So there will not be a single-sex, single-gender crew going to the moon or to Mars. We need to really examine this, and we've done significant strides. We've conducted significant research in how we improve team effectiveness. One of the issues that is often brought out, and we talked a little bit about this, is how do men and women interact differently to technologies? Well, we know every single element of technology, men and women have a different response. It's really important to see the world through a sex-gender lens, and that is what my nonprofit does, which is entitled iGIANT. It's an acronym for the impact of gender and sex on innovation and novel technologies, and we're an accelerator for gendered innovation. And we look at health, IT, transportation, and retail to see how men and women interact so that we can develop better design elements so that we can improve work performance and be able to live safely and well. And I think just in conclusion, as we talk about going to the moon in the 2020s and to Mars, I like to believe that the next boots on these surfaces will be worn by a woman, and we will be sure they will fit her.
You are part of this conversation. We do have 2 microphones in the aisles. If you want to start queuing up there, we can take your questions. Julie, I actually want to start with you. You talked about the 5 hazards of human flight. As you started to do those swim lanes, as you called it, do you separate them kind of into bio and behavior? Can you make it that simple, or does it really need to be separated out so you can find the differences and the nuances between them?
Well, the interesting challenge for us is those 5 hazards of human spaceflight are one independent set, and then you've got the traditional scientific disciplines that study human health as a different set. And in fact, they intersect in complex ways, in kind of multidimensional ways. So for example, radiation does not just affect physiology, it does not just affect psychosocial aspects. It really has to be thought of comprehensively. It also affects the microbiome, so it also affects the environmental aspect. So one of the things that we do to help in approaching that better is to use systems approaches, both systems biology as well as systems engineering, actually together, to better understand what are the needs of the human system, how do we input new information as we gain it, and into a medical model so that we have a good model of medical care, and then we can update it as new medical technologies become part of the menu of things that we can select. And that's, I think, really important because 20 years ago when the Human Research Program, or 15 years ago when the Human Research Program was set up, it was really thought, okay, well, the physiologists will work on these risks, and the behavioral medicine people work on these risks. And that's really not how you can do it today, as we know a lot more.
Dan, as you look at an emergency room or a hospital, and we think about all of us being future space travelers, are we healthy enough to do that? We want to send the best and the brightest and the most fit in those early days, but what do we as humanity need to be working on? I am basically a giant bag of goo, essentially. I don't work out, I'm really sedentary. So if I want to go to space, what do I need to be doing now to really build up my muscle tone, my bone structure to be considered?
So one thing I've learned working in an emergency room is humans can do a lot of stuff. And they will be fine most of the time. I'm there for when they're not. And so it kind of comes down to what risk is everyone willing to take to do these things. As I said, I work in an emergency room, and we've all seen the internet. People are willing to do a lot of things that is probably not the best for them to do the things that they want to get done. And so my concern as a clinician is not really the first couple missions, because the amount of pressure, like it'll get done, it'll get accomplished. It's more the sustainable, which happened with like our original lunar plans in the U.S. is how do we keep people there to do stuff? And then it doesn't matter how healthy you are. If you're working in an industrial environment or an operations environment for an extended amount of time, you will get sick, you will get hurt, you will do these things. And so the best thing to be prepared as anybody who wants to go do this stuff is just to know your body and what you're capable of doing. And so you're able to say, this is not something I'm able to do, so you don't put yourself in a situation to get hurt that requires other resources to do it. So I think people who are deconditioned, who are big bags of goo, you have less to decondition if you're out flying in space. And so you're gonna be operating more at your normal capacity, as opposed to if we're sending high-performance athletes, and I don't mean that personally, but, if we're sending these high-performance athletes who are suddenly now in bed rest and equivalent, they have further to lose in muscle mass stuff, which is why they spend 2 to 3 hours a day working out to maintain their homeostasis. That's a lot of time as a mission planner to take out of the day for do it. And so if you have people who are willing to do be less fit while they do these things, then you have other problems about what they're going to break or what they're going to get hurt of. But I think just recognizing what you're able to do and what that impacts the overall mission is kind of the key to that.
Saralyn, you want to add?
Yeah, a couple things. Well, and this is where I think the private sector, the commercial space sector, is going to play an important role, because we've democratized space. Everybody potentially will have a chance to go and explore. And I think we're going to learn a great deal versus sending our super athletes or specimens that are so well trained. And I think people who look like us will be able to see how well they can manage and how well they adapt and how well they do when they return. We're also entering an exciting world of what I call Astra Omics. It's precision medicine in space. We certainly have it on Earth with the All of Us study, the Precision Medicine Initiative that's been launched by the NIH. And when we're able to go into space and we're able to actually tailor our countermeasures looking at the individual, I think we're going to have extraordinary success as well. So we're at that beginning phase. We've had the one-year mission from Scott Kelly. We have 2 extended missions for 2 of our female astronauts to come, and we'll learn hopefully a great deal from that. And I think that gives us important messages for all of us that we can go into space, we can tailor our countermeasures, we can do well, and we can successfully come back to Earth.
Wonderful. Yes.
Can I just throw
Sure,
one
please.
little wrench into that, particularly for the
Please
emergency room guy, and that's it. What if people get sick and you have to figure out if it's a Mars-related illness or if it's just an illness related to exposure to this unusual and confined environment? I mean, because we don't talk much about the possibility of quarantine, but quarantine on Mars could be a very difficult sentence.
Julie it sounds like Julie has an answer maybe for
Yeah,
you.
so one of the really neat collaborations that's been going on the International Space Station is a collaboration between folks that are planetary scientists and folks that are microbiologists, and we've been testing genomic methods of quantifying and measuring the bacteria that are living inside the International Space Station. Those sequence-based techniques give you the ability to see all the organisms that are there, not just what you can culture, which is the old-fashioned way of checking the cleanliness of your spaceflight, right? Was to swab things down and see what grows on a blood agar plate. Well, that's not as informative as knowing sequence-wise what was really there. And those become multi-purpose tools. So that kind of a sequencing technology, and some of these are this big now, and they only take very little time to run. And so you can use that technology, you can use it to evaluate the cleanliness, what's in your spacecraft, you can use it to determine if a crew member has say a urinary tract infection, you could use it to determine what kind of organism that is. And you can use it as your planetary protection tool to be confident that, that you know what kind of organisms you're dealing with in that environment. And the fact that those planetary scientists and microbiologists are already collaborating at Johnson Space Center, I think is just a great partnership.
Which works well if it's very Earth-like life, but if it turns out it's something that can replicate, but it's not entirely Earth-like, then do we have the tools? Are we ready?
Right, and that's one of the questions that they're working on. For example, Astrobiology had a paper published earlier this year where they identified some molecules that could have been part of DNA, biochemically,
XNAs.
but are not, the XNAs. And one of those sequencing technologies should be modifiable and be able to detect those. Other sequencing technologies out there are not. So that's why I think that's just a really great synergy area as we look forward to going to Mars.
Ruth, I want to have you weigh in on that, and then I want to go to the questions.
Yes, okay, because I would like to add to Saralyn to transition back to Earth medicine, because what is an astronaut? It's a healthy man, woman we send to space, and in a very short time period, she will experience things which we experience during aging, so muscle, bone loss, immobilization. So bringing back these experience, understanding the mechanisms, what the impact of gravity, what we need for training. We have all kinds of diseases on Earth where we can use it. Looking at bed rest, the changes in the eye, the visual system. It might be that if you put the bed up the head, so a change in pressure, it would also help in the medical things on Earth. So I think transition back to Earth is also a very important thing which we have to bring in our study to explain why we are doing this kind of space study.
Our first question over here. Go ahead, sir.
Yes, good morning. My question is probably for Julie, and for the problem of the isolation and confinement environment that the astronauts would feel to and from Mars. Have you considered maybe opening up the internet so that they can communicate with the internet, not just to Houston, but not just to DC, but to all parts of the world, so that a citizen of the world, for instance, could have some kind of conversation with an astronaut in transit, especially for the first mission? And that would not only engage the astronauts and give them some mental activity as much as they want, probably, but it would also engage the citizens of the Earth in terms of being able to actually talk to astronauts on the way to Mars. The downside of that is that by the time we have a Mars mission, the population of the Earth will probably be around 9 billion people, so there was a little traffic congestion there, perhaps. But,
well, so there are two aspects of that question that I want to unpack. So the first is the perception that crew members on Mars missions can't communicate, or crew members on our missions today, for example, can't communicate. And the fact is that they do. So we have satellite phones. They can call their families every day if they want to, and sometimes they do when their families are in crisis. I get phone calls from crew members on orbit with a quick question. So our crew members on ISS today, and they do have access to the internet. Now we do some things for IT security purposes, so we don't just have it open band everywhere. It's not just another node like any other node. We protect it. But those things are available, and they will be available for a Mars mission as well. The difference is the comm delay. So that as you get further and further away from Earth, you have to switch to store and forward communications. That's not necessarily bad. And as an example, I have a teenager, a 17-year-old, and I use store and forward communications with her, and I bet many of you do as well. It's called texting. And that is the primary way I know that how she's doing. It's how I help solve problems. It's how she checks on things. And so that works really well. That works well for humans. So some of those things, those tools will be really used very much the same way as we use them today. I think the other thing that we have the ability to do is to use the developments in AI and in information technology to have our systems more autonomous. So the big change is that you're not going to say, hello, Houston, we have a problem, and let the people on the ground solve the problem for you. You need to have all the tools to solve that problem for yourself on orbit, because you don't want to wait 20 minutes for them to go, hey, I didn't hear that. Did that break up? And so it's a change in the way we do our operations. It's not necessarily as different sometimes as we think.
okay,
Another
thank
question
you.
right here.
I have another.
We're going to move actually on because
yes,
well,
but
we'll
I'll
come
talk
back
to
to
you
you if we
later
have time.
about another
If we have
question.
time, because we have a lot
Quick
of questions.
question for
I wanna make sure
Dr.
we
Dan.
answer.
You mentioned a book available online. Could you provide the exact title and author list?
It's a very long title, but it's the Rosetta. The easiest way to find it is the Rosetta Stone project, and it's on the NASA Technical Report server. And so I would do a Google search for
Your name and Rosetta Stone.
Yeah,
There you
Rosetta
go.
Stone, and Richard Williams is the lead author of it.
Excellent, thank you. Yes.
Hi, so my question pertains to what I assume is a very involved and significant recovery period that astronauts coming off the ISS experience, and my assumption is that that includes checking out, making sure they're okay, and also studying any changes that have happened in that individual's body or psyche, etc. When astronauts land on Mars, they will have been in space for approximately 8 or 9 months, and they will have to go through a similar recovery period that we hope is quick enough that they can utilize their time on the surface as much as possible, and that will have to be remote and autonomous in some way. So I was wondering if you could talk to the duration and complexity of the current ISS recovery period and how you foresee that changing on Mars.
What can we learn from past experience that can take us forward?
Yeah, so what we've learned from ISS, and this is one reason that we have a series of missions coming up where we're going to have very structured different lengths of mission. So you've heard about Scott Kelly's one-year mission. We have a couple of crew members who will have extended missions in the near term, but over the longer term, we have a structured set of studies where we'll have 10 one-year missions, plus 6-month missions, plus 6 to 8 week missions in a pattern so that we are able to well characterize the effective mission duration on this immediate post-flight transition period. We also will be doing a set of studies that build on what we're doing in Kazakhstan today, where we look at the performance of the crew for the first 10 hours after their landing and evaluate what kinds of mission activities they could do and which kinds of mission activities does it take a little bit of time. But the good news is that you've got to focus on some of those near-term gravity transitions and their effects on the crew. But the human body is extraordinarily resilient, and these crew members start recovering their capacity quite quickly. So by the time we do our post-flight baseline data collection on ISS crew members, usually about 7 days out from their landing, many of the disruptions are starting to return to normal, and they're certainly able to do normal kinds of activities. You or I would interact with them and not really perceive that they'd been on a space mission anymore. So sometimes people will focus on the problem. The problem is an interesting problem, but the risk can be managed through countermeasures, through training approaches, and through the supportive approaches that we have in our technologies in our landing systems as well.
Ruth?
Yeah, I think a lot can be done in the countermeasures, and we at the NB Hub, we have the direct return of the ESA astronauts, and it was fantastic seeing Alexander Gerst after the mission. He really ran around as nothing happened. So I think that they have a very high motivation for training, and even it's not enough. We see still a muscle and bone degradation, but I think therefore we need the testbed ISS to continue on the research and to guarantee that they stay fit.
Sir. You're up, orange jacket.
Hi, my wife's a medical doctor. She practices at a facility in Northern California where Dr. Mark used to practice some years ago. She comes to these conferences sometimes and complains there's not enough about space medicine. I'm glad you're here. Okay, the question is this. We put these 6 alpha top 0.5% people, perhaps from different countries, different cultures, different religions, in a tin can for all this time, and we send them to Mars, and all these psychologists are pulling out their hair saying, how can we predict who's going to go nuts during that 18 months and commit murder, you know, regardless of all the psychological screening.
That's a leap there, okay.
All right. In the late 70s, I was at the Prudhoe Bay, you know, the Alaska pipeline, and the predecessor of British Petroleum did something incredibly innovative when they set the base up there. There were 60% male employees and 40% women. All right. The good news is the men started dressing nicer, their hygiene improved, very little bad language and machista behavior. The bad news was sex happens between people, and sometimes you would have a situation, for example, where 2 men would be interested in 1 woman, okay? And let's go one step further.
Can I ask you what your question is?
It did happen. Later on, I gave my son a book called Sex and Space.
Yeah, I was going to say, you're writing a great book that I look forward to reading. But
okay, no, it's already out. Okay, all right. And then Dennis Tito, when he was going to do a Mars orbital mission, he came up with something original. He was going to pick a domestic partnership or a married couple, whatever, somebody who had been together many years and was compatible and could most likely survive together in that tin can all that time. The big question is, how do we pick those people to make sure that there's not some disastrous blow up during the mission because of whatever, you know?
I think that, you know, when I look at shows like The Bachelor and The Bachelorette, you know, that's a different way of choosing people for an outcome. So Ruth, when you're doing research on isolation and team building, you're using that same technique of casting, but in a very different way for teamwork. That's what you're looking for. So tell us how you choose people and anybody else who wants to weigh in on the selection process.
Well, it's a very hard selection process because we have to be sure, even in the 6 weeks bed rest, that they really stay in bed and not after 1 day said, wow, because so it is a very hard selection, psychological and medical things, and to be quite sure that we have chosen the right ones.
Right. Anybody else want to weigh in? Saralyn?
So what you were referring to regarding Dennis Tito's program, it was called Inspiration Mars, and we had actually had work groups developed to address some of those issues that you were bringing up. I think crew composition is extraordinarily important. It's not only who is there, but it's the size, it's the multicultural component of it. So there will be a great deal of effort that will go into it. I'm a geriatrician as well, and I've often suggested maybe we just need to send older individuals. There's level of maturity, the latency issues for cancer is a little different, and then we could get ARP to sponsor or co-host that. And I say it in a jocular sense, but I also want to ensure that it's not just young people, that we really look at it from a multi-generational component, and that we bring part of Earth with us, and that involves the generations. So I think this is an avenue for a lot of discussion and hopefully input from our private sector as well.
We're running out of time. I'm going to go to Lisa last, and I know there are questions. At the networking break, we will all, I believe, still be here, so we will be out in the grand hallway for you to continue asking questions, as well as using social media. I think our last question goes to Artemis.
Okay. I want to know whether women are better or worse based on the fact that my immune system as a female is far more aggressive if something attacks me. I've learned that if I have a flu vaccine, and I'm one of these persons that's always vaccinated up to the hilt in anything that you can get, because I do travel a lot and I don't want to attract polio or something. Anyway, I know that I can only do half a dose because otherwise my body might overreact and I might develop an autoimmune disease. So back to my questions. Are women, because of this immune reaction, better suited to travel in space or less suited?
Artemis, you're bringing up something that's very important, especially to our health on Earth, and I just want to take a minute to highlight what you just said. Women have very robust immune systems. That's why 70% of autoimmune diseases are more common in women. Women tend to also be more resistant to infection, but once they are infected, they mount very robust responses, and then the issue gets really complicated when you're pregnant because of all the immune issues with that. We so far we've seen certainly immune system changes. As we mentioned, there's like accelerated aging in space, and what you would see in the older population, you tend to see in space as well. In regard to those sex differences, we haven't really seen any true sex difference at this point. We do have from Scott Kelly, he was vaccinated in space, he mounted a very good response. So hopefully as we have these extended missions with our female astronauts, we will see this as well. And then hopefully that issue will be taken off the table. But we were concerned because, again, the immune system is so critical to overall health. And again, you are right, we have to look at dosages for vaccines on Earth, and we have to be aware of these issues for our own terrestrial health. So there are major lessons to be learned.
Julie.
Yeah, I just wanted to add, as we move on Earth-based medicine to a period of personalized medicine, some of these gender-based kind of assumptions are going to be breaking down. So soon we'll know what kind of immune response different individuals are doing, and we'll be able to personalize our medicine to those particular individuals' needs. That's especially true also when people sometimes talk about spaceflight as aging, accelerated aging. And it's not. It's its own thing. It's the removal of a gravity vector and then the restoration of a gravity vector on healthy people. They react and respond quite quickly. We know how to exercise so we don't lose bone. In fact, NASA doesn't consider that a red risk for Mars anymore. It's because we know what to do to keep people from losing bone and muscle and to be able to be healthy and be able to carry out some rigorous EVAs when they get to the surface. So I think it's important to recognize that the human diversity is such a key part of the way that we design our missions. It's going to be a part of the way that we care for the crew as well. And it helps us, we'll be able to tune the ways that we respond and protect human health so that we're able to successfully complete those missions.
Thank you so much to our panel, Ruth Hemmersbach, Julie Robinson, Dan Buckland, Lisa Pratt, and Saralyn Mark for this incredible conversation. Again, we'll all be out during the break in the main hall to answer the remainder of your questions. And thank you for your fantastic questions.